Hello, and thank you for joining the AEPA Module 2 Unit 1 course on EVSE standards and communication protocols. Electric vehicle supply equipment, or EVSE, also commonly referred to simply as a charger, rely on standards and communications protocols to maintain safe and reliable operations. Today we'll be discussing EVSE technical standards relating to both the vehicle and electric grid interactions. Additionally, we'll be discussing modern vehicle communication protocols relating to the vehicle, charger, and network operations. To begin, we'll start by discussing each of the different EVSE standards and codes that relate to the equipment side of electric vehicle charging and how that interacts with the grid. There are many different standards and codes, but for this course we'll be discussing three key terms, starting with a standard, which outlines the design for a certain product. For instance, the Society of Automotive Engineers J1772 standard outlines the design and operating conditions for EVSE. This ensures that a charger is compatible with a specific vehicle and provides reliable interoperability. A certification ensures that a product is manufactured according to a standard. This is sometimes referred to as a proof of quality and will let the user know a product is safe to operate because it was built according to the relevant standards. Codes, on the other hand, deal more with the installation of equipment. The National Electric Code Section 625 outlines specific installation rules to ensure the EVSE will operate safely and support grid reliability. The development of each of these three elements is an important role for policymakers. A national system of standards and codes will create a safer and easier environment for drivers and will support interoperability between vehicle manufacturers, resulting in more consistent infrastructure such as public charging stations. As discussed, a well-designed system of standards and codes creates many benefits for all stakeholders involved. Consistent designs make investments such as vehicle manufacturing or the installation of public infrastructure much more predictable. However, constantly changing designs or many different types of chargers would result in confusion and frustration for both companies and drivers that would have to keep up with many different variations. The system also supports the highest quality products because of the certification process, which promotes consistent and durable products, ensuring all of the standard requirements are met by every manufacturer. Additionally, well-thought-out designs and appropriate installations also ensure EVSE work well with typical grid operations and support grid reliability through benefits such as overload protection or ground fault detection. Each of these benefits also promote a safer environment for all drivers operating charging equipment. However, this system of standards and codes requires a concerted effort, meaning that each element should work with and refer to the others. For instance, in the designs outlined in a standard, both the certification process and installation requirements must be understood. Similarly, the certification process will typically detail test procedures that must understand the designs of a specific standard and will make sure those tests account for the requirements outlined in the installation codes. Finally, the installation codes will typically refer to specific standards and certifications to ensure the appropriate equipment is being used. Here's an example of how common EVSE standards and codes in the United States are interrelated. Each one must refer to the other in order to ensure their requirements are relevant to the entire system. Although some of these references may seem redundant, the precise language in these documents is essential to create a successful EVSE environment. In addition to the standards and codes in the United States, there are also many other examples from other countries. For example, the CHAdeMO standard, developed by the Charon organization, outlines a DC fast charging standard common throughout the world. Additionally, some other standards are more regional, such as the GBT standard in China or the IEC standard, which is most common in Europe. After discussing all these documents and all the benefits this system of standards and codes may create, you might be wondering, where are standards most important? And to answer that question, we'll be discussing two different environments, particularly the environment between the charging station and the vehicle, as well as the environment between the charging station and the electric grid. To start, look at the environment between the EVSE and vehicle connections. As discussed, there are many different types of standards. For instance, the North American SAE J1772 standard, commonly referred to as Type 1 internationally, offers two different charging port styles. One is specific to AC charging and only requires 5 pins. These charging options are typically referred to as Level 1 and Level 2. In addition to AC charging, there's also a DC charging port design that requires 2 additional pins, counting to 7, and is referred to as the Combined Charging Standard, or CCS1. Contrary to the North American options, in Europe and other emerging markets, the IEC standard is most common. This is actually sometimes referred to as the Type 2 charging port. In this, the AC charging port has 7 pins, and the DC charging port has 9 pins. Also, you can see there's 2 additional pins required to support that DC charging port, and in this instance, it's referred to as CCS2. It's important to know that AC charging uses grid power directly, and therefore the electricity is passed directly from the grid to the vehicle, with the EVSE simply monitoring the flow of power and ensuring a safe operating environment. However, the DC charging options must take this AC power from the grid and convert it into DC power to put energy directly into the vehicle's battery. This is what enables typical higher charging power levels compared to AC charging. And additionally, all chargers require simple pins for communications and controls, and these additional pins are how those safe environments are operated, and many features such as fault detection and overloading protection are operated through these environments, as well as the ability to ensure that there's not too much energy provided to the vehicle's battery. While EVSE standards outline specific charging port designs, they also detail the specific power level that is delivered to the vehicle. For each of the SAE standards, there's typically a range of output power that is permitted. The AC charging level 1 and 2 offer a wide variety of output power options based on the operating voltage and maximum current. Level 1 options are the lowest power options, and in this standard also provide the simplest installation process, with 120 volt outlets readily available in most homes and commercial buildings. Level 2 requires a higher voltage service from 208 to 240 volts, which is also common but may require more expensive installation costs. Additionally, because DC charging must perform voltage regulation in the EVSE, it is capable of receiving a wide range of input voltages. It's also important to note that a standard may permit a higher power than is available in every location. Under these circumstances, you must rely on proper installation codes to ensure a safe and reliable installation. You might be wondering what those power levels mean and whether or not they're always relevant. And for many EVSE, they do not always operate at the highest power output. There's many different reasons why this might be the case. But for installation requirements, a circuit breaker sizing might limit how much current can flow, or you might have limitations in your service panel capacity. Company design differences might also create lower and higher power output options, and vehicle limitations such as the onboard charger and battery DC voltage can limit the peak power that the vehicle can receive. However, for AC level 1, a broad assumption is that if you're delivering 120 volts, it's very common to also get 12 amps. That will be about 1.4 kilowatts, which in most vehicles will equate to about 5 miles of range in 1 hour of charging. For AC level 2, you can see there's a higher voltage at 240 volts is very common, and 32 amps. This results in 7.7 kilowatts of power delivered to the vehicle for an average of about 25 miles of driving range in about 1 hour of charging. DC options can range widely based on battery voltages and how much current the battery can receive directly. However, in general, a 50 kilowatt DC charger will deliver about 100 miles of range in about a half hour charging, and DC level 2 oftentimes will be about twice that. It's important, though, with DC fast charging to understand that with AC charging, you're always receiving the same power output. But for DC charging, as you can see on the curve on the right, that peak power output is only delivered during a period of the charging session. This small period is dictated based on the battery state of charge, and lower power outputs are specifically designed at the ends of the state of charge spectrum, as you can see low and very high states of charge, in order to protect the battery and ensure it has a long life. In addition to the power level requirements, the SAE standard also outlines charge port designs that create a consistent environment between the EV and EVSE. The most important of which is probably the physical dimensions. These specific physical dimensions ensure that the charger and vehicle charge port are always compatible. Additionally, the vehicle connection and pin design must be very specific in order to ensure each pin that should deliver power or communicate to the battery is designed appropriately. Finally, the environmental and durability needs are incredibly important to ensure temperature and moisture conditions, as well as installation of the handle to protect the user from voltage, are done so to create a safe operating environment. After establishing the power requirements and charge port connections, it is important to understand where the energy goes. For AC charging, AC power travels through the EVSE and to the vehicle's onboard charger. The onboard charger must then convert AC power to DC power before it is delivered to the battery. This simple charger design typically results in lower cost EVSE. While DC charging, on the other hand, must convert AC power to DC power within the EVSE before it can be delivered directly to the battery, bypassing the onboard charger. Performing this conversion in the EVSE typically results in larger and higher cost EVSE, but also permit higher power charging. All DC charging and most AC charging, with the exception of IEC Mode 1, provide safety features that operate during every charge session. These operations typically occur within the EVSE. However, in the case of portable units, such as SAE Level 1 or IEC Mode 2, there is a device in the middle of the charge cord, sometimes referred to as the In-Cable Control and Protective Device, or ICCPD. These safety features communicate directly with the vehicle and ensure proper connection with proximity detection. They also will communicate with the battery using a handshake to ensure it is not overcharged and will stop charging if a ground fault is detected. In addition to the vehicle connections, it's also important to understand how the EVSE interacts with the electric grid. This environment between the grid and EVSE is typically detailed in installation codes. For the United States, the National Electric Code, Section 625, details specific requirements for the installation of EVSE. The most important of which is probably the branch circuit requirements, where each permanently installed EVSE must be supplied by an individual branch circuit with a single circuit breaker designed for overcurrent protection. That overcurrent protection in the circuit breaker must be sized for 125% of the maximum EVSE load. Take, for instance, an EVSE that's designed to supply 32 amps to the vehicle. The circuit breaker must be sized to protect 40 amps in accordance with the NEC requirements. In addition, the conductor gauge and length typically have guidelines on their sizing and maximum distance from the service panel to the EVSE. For instance, level 2 generally is accepted number 8 wire gauge and less than 25 feet are sufficient to avoid excessive voltage drop. In addition to these requirements, a loss of primary service is a concern for specific EVSE that are capable of bidirectional power, in which vehicle may come off of the battery on board the vehicle through the EVSE and power a home in the event of an outage. However, if there is a loss of grid power, these type of systems must not backfeed into the grid and therefore may only operate on a specific microgrid environment. NEC requirements, as well as common electrical equipment ratings, have a strong influence over installation practices and EVSE options. For instance, portable level 1 units typically operate below the maximum permitted power, such as 12 amps for a power of 1.4 kilowatts. This is because they typically plug into 120 volt receptacles on a circuit where the other devices may be operating. If these devices were too powerful, it could trip the circuit breaker and turn off the lights and devices in that room. Alternately, permanent level 1 units typically operate at the maximum 16 amps for a power of 1.9 kilowatts. This is because they will have a dedicated 20 amp circuit breaker oversized by 125% according to NEC guidelines. The most common level 2 power options are also influenced by common equipment options. Although the standard permits devices to operate at maximum 80 amps, this would require a 100 amp circuit breaker, which is not very common. The most common option is a 32 amp level 2 EVSE that is properly installed with the typical 40 amp circuit breaker. However, The power delivered to a vehicle from these devices is also dependent on the voltage service. Level 2 units may operate with either 240 volts, common in households and resulting in 7.7 kilowatts of power, or may also operate at a lower voltage of 208 volts, commonly found at commercial businesses, and would deliver a slightly lower power of 6.7 kilowatts from a 32 amp device. DC fast charging devices may operate under a wide range of input voltages and typically require three-phase power. Also, because these devices may take DC voltages as an input, some utilities are considering providing customers with DC voltage services in the future. In addition to the vehicle and grid connections, modern vehicles that have communication standards for third-party networks also require specific protocols that detail all of this external communication. There are three different levels of communication we'll discuss in the next few slides. The first of which is the vehicle communication, in which the vehicle communicates to the EVSE and the EVSE communicates to the vehicle. This is important to understand battery state of charge as well as how safe the grid is operating. Charger communication standards, on the other hand, allow data to flow from the EVSE to a network communication. This is typically to enable third-party data management operations or smart charging. Finally, network communications oversee the flow of data throughout third-party data providers. Many devices within the vehicle require different forms of communication. For instance, you might want to turn on your windshield wipers or lock the doors. In addition, you might also want to see the state of charge of your battery and how much power it's receiving while you're in the vehicle. All of this type of communication can occur over the CAN bus, or the controller area network. This is an in-vehicle communication protocol that oversees the operation of many different vehicle functions and data sources. This is a very common communication protocol that speaks with the CHAdeMO charging standard. Access to this CAN bus is typically provided through an OBD2 port, or onboard diagnostics. This provides access to the CAN bus in order to perform diagnostics such as mechanical or maintenance challenges, and is also very important in telematics to record driving data. In addition to vehicle communication, there are also many important EVSE communication protocols. ISO 15118 from the International Organization for Standardization deals with communications between road vehicles and the grid. This standard is used by the SAE CCS DC charging standard to support communication between the vehicle and the EVSE to ensure a safe charging environment for the battery. The protocol also enables plug-and-charge capabilities that create a more streamlined transaction process for public charging, which bypass the need to swipe a credit card. The OCPP, or Open Charge Point Protocol, is incredibly important to enable communication between an EVSE and third-party network provider. This enables smart charge controls to be provided to a wide range of EVSE types and supports interoperability. Finally, there are also protocols regarding the communication between network providers. The OCPI, or Open Charge Point Interface, supports inter-network communications and is primarily used to enable roaming. This is useful when Company A's app is paying for charging done on Company B's network. Additionally, IEEE 2030.5 from the Institute of Electrical and Electronic Engineers is crucial in the development of smart grids and supports communication between DER, or distributed energy resources, such as solar systems, backup batteries, or vehicles with bidirectional charging capabilities. This communication will enable the use of smart charge control strategies to provide grid services such as demand response. Thank you very much for your time, and please feel free to direct any questions you might have to the contacts listed here.